In this video, we'll be looking at a practical problem that seems difficult until you introduce a new and very useful mathematical tool. Then, a whole range of related problems suddenly become approachable. Say that you are a stonemason working on a tapered column. You know the next step is going to be carving a design into the column's surface, but when you get the design from the architect, the art is drawn on a square grid. If we try to transfer the design directly to our column, we can see that this isn't going to work. A square grid doesn't fit neatly on this curved surface. Apparently foreseeing this difficulty, the architect has also handed us a new tool to help with the project, but it's just an unfamiliar pair of letters, so we'll set them aside for now. So, where do we start? You could try freehanding the art, and with a lot of hard work you might get a passable result. But the architect has very precise standards, and would like your carving to match the design as perfectly as possible. In other words, we need to figure out how we can somehow transform our design so that it fits exactly over our column grid. This may seem like a daunting problem, especially because we're dealing with a curved surface in 3 dimensions. So let's try to simplify things by unrolling our column so we can work with a 2D surface instead. This is the surface of our column. Compared to the square grid, it looks a bit more complicated. But at least now we can better visualize how we're going to have to transform our art. Somehow, we need to turn this shape into this shape. And to do this transformation exactly, we'll need to be able to talk about our grids and the points on our grids mathematically. Describing points is easy on our square grid, which we'll say is 100 units wide and 100 units tall. On this grid, each point can be described by an x value and y value. Horizontal position defines a point's x value, and vertical position defines a point's y value. But looking at a curved grid, things don't seem so easy. Let's look at where we want this point on our art to show up on our column surface. What kind of values can we give to this point that would let us, say, take x and y values from a rectangular grid, run them through some function, and get back the corresponding values on our curved grid? Especially if we want that equation to work not only with this column, but with any column we might be carving on in the future. To answer this question, we need to realize 2 things about our column. The first is that any tapered column can be thought of as the bottom of a cone, like this one. As with our column, let's unroll the surface of our cone to get a better look at its shape. The second thing we need to realize, which might seem intuitive now, is that the surface of any cone is actually a section of a circle. I won't go into a proof of this here, but if you play around with some paper and scissors, I think you'll be able to quickly demonstrate this for yourself. So, where does this get us? If the surface of our column is part of the surface of a cone, and if the surface of a cone is a slice of a circle, then for any tapering column we can think of, we will always be able to find the surface of that column arranged on the edge of some circle. Or, if we think of drawing it, on some circular grid. And here, finally, those mysterious letters from the architect will come in handy. These are what are called polar coordinates, r and theta. They are like x and y, but describe points on a circular, or polar grid, instead of a rectangular one. Given a point on our circle, r is the length of the line drawn from the center of the circle to that point, and theta is the angle of that line measured off the grid's axis. In this case, we want to align that axis to the edge of our column surface. This is also a good time to note that mathematicians usually express theta in radians, but for familiarity's sake, we'll be using degrees instead. Polar coordinates give us a way of describing points precisely on our column surface, but they have another property that makes them especially well suited for transforming our design. Let's see what happens when we change only the x value of the point on our rectangular grid. As we can see, changing our x value only affects our theta value. And if we change our y value, we can see it's only affecting our r value. This very clean relationship between our variables makes it much easier to figure out how our r and theta values are determined by our x and y values. And how are they determined exactly? With a little effort, we can work out these equations for our polar coordinates. R here is equal to the radius of the big circle we found by unrolling our cone, minus y divided by the height of our rectangular grid, multiplied by the height of the column surface. And theta is equal to our x value divided by the width of our rectangular grid, multiplied by the bottom width of our column surface, divided by the circumference of our big circle, multiplied by 360. Now, these equations take some work to derive, but once you have polar coordinates in your tool belt, it only takes basic algebra and geometry to figure them out. It's a nice exercise if you want to prove this for yourself. So, now that we have our transformation equations, we can go about transforming our art. Let's start with a single point as our test. This point is located at x equals 80 and y equals 100. Let's plug our x value into our equation, and our y value, substitute in the other values specific to this column and grid, and compute the results. According to our equations, a point at x equals 80 and y equals 100 on a rectangular grid will be represented by a point at r equals 200 and theta equals 15.26 degrees over on our polar grid. Let's see if that checks out. And there's our point, right where we wanted it to be. Now, if we can transform one point, we can transform 1,000 points. Let's take our art and break it down into a set of many small points. If we begin running the x and y values of all these points through our equations, well, let's see what happens. And there we have it, our transformed art. Let's see how it looks on our column. A perfect fit. And because we found the general form of our transformation equations, we can fit the art to any tapered column we want. There's a lot of chiseling ahead of us, but for now, let's set down our tools and appreciate some very clean line work.